Hello, Libuseng, can you hear us?
Yes, hello, can you hear me?
Yes, perfectly.
Okay, let me just set up my presentation. Okay, um, can you give me just a moment?
Speak with the control the computer. Really. No, you can, yeah, just up the volume maybe. It seems good.
Hi, everyone, can you hear me?
Yes, I can hear you.
Okay, I seem to be having trouble sharing the document. But let me see, I think it will work now. Please do let me know when it shows up on your screens.
I can see something. But it's sort of a black blob at the moment.
Let's see. Is the screen still blank?
Yes.
I think what I should do, Robin, I should email you the document and then you can share it for me. Can we do that?
Yes.
Okay. Okay, let me just.
Oh, Microsoft, don't let me down now. Okay.
Okay, I've sent it, Robin. Have you received it?
Speed typing? Caps locked.
It's not there yet.
Not at the moment.
The start number is correct, right?
Then why is it taking me?
Why is it taking so long? Because I see it here.
Yeah, we're just trying to sign into
To the computer.
to Outlook. We don't have the same.
Okay.
It's normally a start number.
Okay.
Caps lock.
Nope. It's gonna be hard to get it from your phone to the computer. Can,
Okay. Let me try to share this my screen again.
yeah, please
Yes.
do, because it's a bit difficult for us to get the email from Robin's email into here.
That's not yet, so
Okay. I think it will let me do that now. Let me just open it quickly. I'm so sorry for all this inconvenience. Technology will let you down.
just gives more time for people to log in.
It really will let you down.
Weird. It's weird that it doesn't. We don't see any screen share yet.
Yes, just give it some time. Okay. Okay, I'm still here. Should open. It's just taking a bit longer than I anticipated. Let's see. While we're waiting, how long do I have to give the presentation?
About 30 minutes is normally 30 to 45 minutes.
Okay, perfect.
Yeah. We first
Okay.
have to see the presentation. That's the crucial ingredient.
Yes, I think it will work out now.
Unless you would like to freestyle with no presentation. That would be impressive.
It would be impressive, but imagery is always important because images help us visualize what we're talking about much easier. Please let me know when you can see my screen.
Right, it seems like something is happening.
Finally.
There is quite a long delay.
Yes, there is. There is quite a bit of a delay. I don't know. I'm not sure what's happening. Maybe the computer is on its last legs. Let's see. Can you still see the screen?
It's telling us that your screen sharing is starting, but we don't see anything coming up. Nothing's really changing. And we don't see your presentation in Robin's email either. So it suggests that it's quite a big presentation.
Oh God. Let's see. Can you still hear me?
There we go. We see something now. Okay, we see your screen. Can you go into full screen mode for us?
I'm trying to, but something is happening here. Okay, let me just see.
Yeah, we can see your slides changing.
But it's still, is it in full screen?
No.
Okay. Okay, can you see everything now? Is it doing what it's supposed to be doing?
It's doing what it's supposed to be doing.
Thank you. I'm so sorry for all this, but we can get right into it. My name is Libuseng Kolobe. This presentation is based off the work I did for my master's project at the Institute for Groundwater Studies at the University of the Free State, and I was under the supervision of Professor Francois Fourie. The project is titled Appraisal of Geophysical Methods Used for Groundwater Exploration in South Africa. So basically, I will just give a brief introduction into the study, the methodology that was used, and give a summary of the literature review, as well as give a description of the study area, and then we'll look at the use of geophysics in South Africa. So basically, groundwater exploration entails looking for new groundwater resources or characterizing groundwater within a specific area. There are many ways to do this. As you can see in this diagram here on the left, this man is holding a forked rod that is used in esoteric methods, which are just can also be called water witching or water dowsing, where people look for water using these means. This is quite difficult to emulate because it is a subjective kind of field. Or we can use geomorphology, where we look at the landforms to determine the areas that best have the greatest groundwater potential, like valley bottoms or places with gentle slopes. Or we could look at the plants in geobotany. These plants can let us know if their subsurface groundwater changes, or we can look at the geology or structural components of the ground, because these determine the groundwater potential quite extensively, as the groundwater is hosted in these rocks. Or we can use geophysical methods that help in the decision-making process when we are trying to find new groundwater resources. So basically, the study is significant to see because South Africa is a water scarce country, and because of increasing water demands, it's important to diversify our supply of water. So in this diversification of the water, groundwater is quite important because it is quite underutilized in the country. And when you're trying to develop new groundwater resources, groundwater exploration is an important step of this finding this human right. We can also see the importance of water in general by things like the World Water Day that we recently celebrated last week on the 22nd of March. The aim of the study was to consolidate available information on geophysical methods used in South Africa by determining methods commonly used for groundwater exploration in South Africa, how the method may be influenced by the local geology, typical structures that you may target during exploration, looking at the physical contrasts of these structures and the geophysical responses that you would expect during a geophysical survey, and also to make recommendations about which methods should be more in use in the country. So the study, it was a desktop study. So basically we reviewed the literature to just give a global picture of groundwater exploration in the international context, and then also to see how we would confine the study area, as well as describing the study area in terms of its geology and geohydrology. Then finally, we looked at published and unpublished reports that relate to geophysical groundwater exploration in particular, looking at the target features that the people reporting used, as well as the methods that they preferred to use. But in this study, there were several challenges that could be met. Most importantly is that reports are not in the public domain, and more often than not, the reports that you would get relating to hydrogeology do not have information on the geophysical surveys. And it's quite difficult to get this information in one sitting, as the information is quite fragmented, and you have no control over the quality of the reports that are generated. So we can just have to take the data as it is. And also people have a bias of reporting the things that they have deemed successful themselves. So for example, if a particular consultant was having trouble in a certain area, they would only avail the reports that showed them being successful according to the criteria that they had used to define their own success. Also, you could find that issues of confidentiality with client information, that it's not quite easy to share that. So geophysics has been used quite extensively in hydrogeology in order to aid exploration. But all geophysical methods, what they have in common is that they exploit physical contrasts in the properties of the earth. For example, a gravity-based geophysical method observes gravitational acceleration due to density differences in the earth. So this illustration here, you can see that when you're conducting your survey, when you reach a body with a higher density, the observed gravitational acceleration would rise. So this could give you an indication of an area that has a greater groundwater potential. For magnetic based geophysical methods, these are based on the fact that magnetized bodies within the ground have a magnetic field that is superimposed on the Earth's magnetic field. So when you're conducting your survey across these bodies, you would find that they are superimposed on the Earth's magnetic field and could cause anomalies with that magnetic field, and they would let us know something that there has been a contrast in the subsurface, and that is the place that you would like to focus on. We also have methods such as resistivity methods, where a current is injected into the subsurface, and then a potential difference is measured here, so that we can give information on the resistivity differences in the subsurface. This can help us determine great areas with the highest groundwater potential, because resistivity or conductivity is influenced by fluid salinity, porosity, and grain size. So we would know that if you see a higher resistivity, may have a lower conductivity, and a lower resistivity area might be the one that you're looking for when you're trying to site a new borehole. Or we can use borehole logging techniques, where a sensor or a probe is put down the borehole to give information on the formations around that particular borehole. There are quite many methods that can be used using this probe, but I'm not going to go into those ones for the purposes of this study. Or some methods could be based on nuclear magnetic resonance. So we know that water contains hydrogen atoms, or a proton, which when undisturbed are in line with the Earth's magnetic field lines. So the basic principle is that these hydrogen protons are excited with an exciting pulse from a transmitter, and then this transmitter will be switched off. And when they switch off, the protons emit a relaxation frequency that is detected by a receiver, and the receiver records the response. The amplitude of that relaxation signal that the protons emit is proportional to the number of hydrogen atoms present, so we can determine the water content directly with this method. Or we can use electromagnetic methods, in which electromagnetic waves are transmitted into the ground. And then if there's a conductor in the ground, this conductor would generate a secondary magnetic field that will then be detected at the receiver and give an indication of the conductivity or distribution within the ground. This can also have a bearing on groundwater potential, because conductivity depends on things such as water content. Or we can use seismic methods. Although these seismic methods aren't really going to show you the groundwater potential directly, however, they can help you determine the distribution of different geological layers within the subsurface, and based on this, we can determine which areas are more likely to be high in the groundwater potential. But recently, because of cost of geophysical methods use, we see the rise of unconventional methods such as groundwater detectors that detect naturally occurring currents within the ground surface. They just put in electrodes into the ground, and then these grounds would measure a potential difference between those two electrodes and would be used to infer the depth, because these currents occur at different frequencies. So from those frequencies, we can determine the depth, and then they create a pseudo section so that we can tell what is going on within the subsurface. There are several uses that geophysics can be used for, geophysical methods in groundwater investigations. This table just summarizes some of them. For example, magnetic methods could be used to delineate dikes or lithological contacts and faults or bedrock topography. But however, you have to be aware that there are limitations, such as the influence of other magnetic bodies or non-uniqueness as well. So you're not really sure, unless you understand the local geology, what is causing these these contrasts. Or maybe something like electrical resistivity that will characterize material, which can be consolidated or weathered, can determine weathered aquifer thickness and water quality, but you could have a poor resolution of targets with a thin width due to transition and layer suppression, and you need a larger area if you want to have a deeper level of investigation. For the study, we also looked at some international case studies of where groundwater, geophysical groundwater exploration was conducted. What is common within these studies is that most of the studies used more than one method. Some were interdisciplinary. For example, in Nigeria, they used lineament analysis, where they used remote sensing data to determine places that had the highest groundwater potential, and then they delineated those places as being necessary for further groundwater, ground geophysical surveys rather. And then in Plain du Nord, they used a hybrid source audio-magnetic telluric method, which is just a method that uses a man-made source of telluric currents, as well as a determines naturally occurring currents in the ground to determine conductivity contrast, and a gravity survey. This image here just shows a modeled basin for that area where the density contrasts that were determined from the survey were used to create this model that is shown here. Other methods that could be used were such as the transient to the time domain electromagnetic method and the vertical electrical sounding, which was paired with a digital elevation model in order to determine areas that have the greatest groundwater potential. Here on the bottom left, we have an inverted TDM data that just shows the number of layers that were present in this particular area, with this corresponding vertical electrical sounding, which is just a kind of resistivity sounding that shows the vertical layering in that area. And these helped inform the making of this well log that was found when they drilled the borehole. So these are just some of the ways that geophysics can be used in groundwater investigation. The study itself is based in South Africa. South Africa is quite a large country. Its climate is semi-arid with an mean annual rainfall of 465 millimeters per annum. This rainfall is not distributed evenly across the country, with the western reaches of the country being drier than the east, which is also good to notice because most of the places that do use groundwater resources are the ones in the regions with the lowest rainfall. The geology of the country is also quite complex, the country itself being in excess of 1 million square kilometers. There are various kinds of geology that you can encounter within the field that all have different characteristics. However, because the country is this quite large, and to try and restrict the boundaries of the study, we chose areas that could be representative of broad classes of rocks that you may encounter in the field. So we chose 9 of these that are listed in the spider diagram here, which were the Kalahari group, the Karoo supergroup, the Barberton sequence, the Namaqua Natal metamorphic sequences, the Ventersdorp supergroup, the Witwatersrand supergroup, and the Cape supergroup, Transvaal, and the Bushveld. These areas in South Africa all have different aquifer types, but we can determine that there are 4 broad classes of aquifer types. We have fissured or fractured aquifers, which are those ones where water occurs in the fractures. We can have karst aquifers or low permeability aquifers, which are which are those ones that are fractured. We have fissured and fractured, which are those ones where water occurs in the fractures. Cast occurs in dissolution cavities, and the low permeability occurs in the fractures. And unconsolidated are ones that occur in unconsolidated formations such as alluvial deposits. All these aquifer types have a different groundwater yield potential. Some have a high potential yield, which could be in excess of 5 liters per second. A moderate potential would be something with between 2 and 5 liters per second, and very low and limited potential would be those with 0.1 to 0.5 liters per second in the groundwater potential. There are some targets of exploration that are used, that are determined when doing groundwater exploration. So these target formations have different groundwater potential, but this is dependent on things such as the lithology of that particular formation. Is the formation sand-rich or clay-rich, like in the Table Mountain, which would be a more sandy formation, or versus something like the Buckeveld, which is more clayey in its nature. So this can determine which formation you're looking for, because something like Buckeveld is actually an aquitard, because it does act as a barrier to groundwater flow, whether the rock is igneous or sedimentary, for example, because maybe sedimentary rocks have more primary porosity than something like an igneous rock. Also, the structures, because the depth of the formation could have a bearing on the groundwater flow directions, as well as the likelihood of water occurring there. But these formations also have specific target features that we can focus on when we're looking for groundwater. This can be the weathered zone, or fractures and joints and fault and shear zones, or maybe dikes and sills or lithological contacts. But basically what these features have in common is that they increase primary porosity, not primary porosity, porosity and effective porosity and permeability, rather. So geophysical groundwater exploration in South Africa has been conducted. It is quite extensively used. They do use geophysical exploration in South Africa, but you would find that publications on the subject are quite scant. So it's difficult to find publications on geophysical groundwater exploration in particular. Also, the level of complexity of the exploration exercise would differ depending on whether it's a local kind of study, a regional kind of study, or maybe whether the geophysics is being conducted because maybe we want to do a bulk water supply or community borehole, or if we're using multiple or single methods, or we're having multiple or single traverses. But this also depends on the equipment available for use, the expertise to operate this equipment, the software to use these equipment and interpret the data, the site itself of the geophysical survey and the infrastructure in the area, because this can have an influence on readings, as well as the time available, because some methods such as electrical resistivity tomography are quite time consuming compared to something like an unconventional method that isn't as time consuming, as well as the amount of money that has been allocated for this particular exercise. So there are several papers that have been published. I'm not going to go into detail about what has been written, the content of these papers, but one of the earliest papers was that from Enslin from 1955, where you could see that he summarized the use of resistivity, electromagnetic and magnetic methods for groundwater exploration in South Africa. And as As with the increase of time, you can see in the 2000s, we now see the emergence of methods such as aeromagnetic methods, with the increasing advances in technology that are available. And then finally, in the present day, we can see that for more recent studies in the 2020s, you now see the emergence of methods of groundwater detectors as they are gaining prominence in South Africa because of their low costs and ease of use. So for this section, we're just going to look at some of the consultant reports that the consultant so graciously provided that were used in the study. You will see that the level of complexity and the detail of the reporting is quite different. For this particular study, the consultant was looking to supply a suburb in Zastron in the Free State with groundwater. So they acquired magnetic data available for the area from the Council for Geoscience, and then they applied it for the specific area that they were looking for. Here you can see that the pinks and reds show higher total magnetic intensity, while the cooler colors show a lower total magnetic intensity. So this black dotted line just shows a mapped geological fault that they took from the geological map available for that area. And then this one here, the dotted pink line shows the mapped magnetic fault, which you can just see with this contrast between the magnetic intensity in these two regions. So they took, the consultant took a survey across perpendicular to the strike of these faults, and then they decided that they were going to conduct a ground geophysical survey in this area, where they used a proton magnetometer to conduct a magnetic survey. And you can see that in this magnetic data, you would expect something like a spike in the magnetic field intensity when you're conducting a magnetic survey in the presence of something such as a dolerite dike. The consultant here interpreted this to be a dolerite dike, and then further down at around 600 meters, you can see that the slight dip that was interpreted to be an erosion channel with leaves, and further at around 1,000 meters, they saw that a dolerite dike had outcropped, and they decided, okay, since we think that there's a potential here at this dolerite dike outcrop, they further conducted a resistivity survey. This is just a modeled resistivity section from a 2D ERT survey, electrical resistivity tomography, where they walked across this area to give a model of the subsurface resistivity section. So you can just see this area of lower resistivity juxtaposed against this dolerite dike shown in the pinks, in the reds, and the purples here in this diagram. So by interpreting this resistivity section, you can see that this area between these two regions would be more likely to have groundwater in it. So it's also quite important to understand the geology of the area that you're working in when interpreting the data, because it's not useful to have this geophysical data but not understanding the area in which you're conducting the survey. Another consultant was citing a borehole for a farm. It was a single borehole, unlike the previous one, which was for a municipal scale project. But basically, they just wanted to cite a borehole for a single farm state here. So they employed 2D ERT, electrical resistivity tomography, across the farm. And this resistivity section here just shows that you have a region of a higher resistivity against a region of a lower resistivity. But if you do not understand the geology of the area, you would think that this area with the lower resistivity is more desirable, when in fact it is this shale from the Bokkerveld, which is not conducive for groundwater occurrence, while this purple here represents the Table Mountain group sandstone in the area. So the sandstone would be a better aquifer than this one. So the drill site was chosen on the side of the sandstone. Here's another report. This consultant here in particular used a magnetic and electromagnetic method in conjunction with each other. These are just this EM34 profile that gives the conductivity differences in the subsurface and a magnetic profile along the same survey line. So they looked at the changes in the magnetic intensity can be seen by these spikes here within the profile. These are also seen by slight increases in the conductivity distribution from the electromagnetic data. The electromagnetic data is just this one that is shown in the red and the black lines, while the magnetic profile is the one shown in the blue line. Some reports do not have a great level of detail within them, such as this one here. This was a survey that was conducted in Umgungundlovu in KZN. The consultant used a water detector, but they did not give further information on anything that was going on, what they used to interpret, or how long that traverses was. So this just shows the great level of difference in the kind of reporting that we do have in the country at the moment. But basically what we can see is that we have multiple methods that can be used for groundwater exploration, geophysical groundwater exploration in South Africa. These methods are often used together. So it's not often that you would find that a survey is conducted with just a single method. But basically what we would look at when we are interpreting the data is a high versus a low contrast. Basically, when we're doing resistivity imaging, we will look at areas that have a higher resistivity compared to areas that have a lower resistivity, and then use the data that you have acquired in order to determine areas that have the greatest groundwater potential. But also bearing in mind that interpretation is specific to the geology of the area. So this is also applied when we're interpreting magnetic maps as well as gravity maps. So for example, if we had an area that had dissolution cavities, a karst kind of environment, you would find that in the gravity map that you would have generated, the gravity images, you would find that the dissolution cavities would sometimes show up as areas of lower gravitational acceleration. Or we can make profiles such as those of the magnetic and electromagnetic profiles, and then look at increases or sharp increases or sharp decreases in conductivity or magnetic field intensity, and then whether they're positive or negative, depending on the local area. But also we can use airborne surveys in order to plan ground geophysical surveys, and this has been done in the country at this point. So in the study, we reviewed around 29 consultant reports and 20 published papers, basically. But what we could find was that the methods were used around 33 times for electromagnetic methods. Resistivity methods were used 25 times, and magnetic methods were used 36 times, which made them the most commonly used methods, while newer methods like the nuclear magnetic resonance and magnetotelluric methods weren't really available in the pool of documents that we did have, and only one method used a geophysical well log. So from this, we can basically see that magnetic methods are typically preferred in South Africa because South Africa does have a large number of dolerite dike intrusions that cover like most of the country. So it makes sense that South Africans would prefer to use these methods when they're conducting groundwater exploration, as well as electromagnetic methods, because they can quite clearly show narrow two-dimensional conductive structures like faults, or maybe resistivity methods where the weathered zone and fractures can be delineated. So these are preferred methods because in most cases in South Africa, you will find one or more of these conditions being met. So for magnetic methods, they would like, they use proton magnetometers. The electromagnetic method, they use the Geonyx EM34 kind of equipment, and the ADM resistivity sets are quite often used in South Africa. So now that we have established which methods are used for groundwater exploration in South Africa, we can find that there are several other things that still need to be done in order to grow this data that we have. But we can say that South Africans do lean towards those three aforementioned types of methods. And it's more important to see the applicability of other methods in South Africa, such as the nuclear magnetic resonance or transient electromagnetic methods, which aren't used as much as the other ones. So it's important to see the applicability in South Africa, as well as to grow the database of geophysical reports within the country. And we can also start to determine the success of these geophysical methods in these different geological settings when we now have enough of the data to create this model. So basically, we need people to build our repository of geophysical reports so that we can determine the level of success of a certain method in a certain area. Also, by predetermining what we declare a successful exploration to be, as well as to find on average, when you're using a specific method, how much that would cost, and basically create guidelines for exploration of groundwater using geophysics in South Africa. Thank you.
Thank you so much, Libuseng. That was fantastic. Really interesting and a very thorough presentation. So from all of us in the room and also the people online, thank you. And perhaps we can open it up for some questions. Yes, I see a question in the chat from Mark. Let's just go there very quickly. Has anyone figured out how the PQWT water detector actually works versus MT? Teresa, can you comment on that for us?
We are not quite sure, but what we think is that maybe a formula of modified skin depth so that we can see how the telluric currents are attenuated, and then they use that to determine the depth. But the manufacturers of this water detector themselves are not really forthcoming with how that water detector works. But there are some papers that are try to see how these water detectors work. I also see that maybe to build the database, we can try the municipalities. Actually, the Department of Water and Sanitation has a geohydrological report system. So some of the reports I got were from that system, but because it's voluntary to upload those reports, getting the geophysical data is quite difficult. But maybe when you approach the municipality directly, that could help.
Okay, thank you. And now we have a question from Sue Webb.
I just want to comment on the PQWT method. I think we have to be very, very cautious because there has been nothing published over a known test site. There has been very little understanding of the claimed physics. And
Mm.
without proper physics and without proper collaborative test sites where you have many different methods over the same geology or test site, I am I would put it in a category where I wouldn't use it myself. So I'm horrified that this is appearing in reports of that are claimed to be good. So I would just caution there, because it's there's a lot of these methods going around that are not physics based, and we see them over and over again, and so we have to be very careful. That's just my comment. Thanks.
Yes.
Yes.
Come through.
Hi, thank you for a very great talk. I thoroughly enjoyed it. Is there any opportunity for our students to come and join you learning about some of this? I think we've got so many companies that are working in exploration and stuff. It would be great to get some experience with groundwater. So if you ever need some extra hands in the field, shout.
Definitely, when I do get the opportunity to conduct further research, I will definitely ask for all the help I can get.
Great. Cool. Thank you again.
Thank you.
Okay, do we have any more? Oh,
Hi, my name is Mary and I'm doing my honors. So yeah, my project is in hydro. So basically it's about the the exploration of lithium in groundwater. So I want to know, are there any reports or investigations that have been conducted? I mean, like geophysical studies that were specifically focusing on mineral exploration in groundwater.
I don't know because I wouldn't really be familiar because I was looking at finding groundwater resources themselves instead of looking for specific minerals within the groundwater itself. However, I'll leave my email address. You can drop me an email and I'll point you into some of the right directions, maybe of places where you can look for that data.
Oh, okay. Thank you.
right. Do we have any further questions from anyone? If not, then it's just left for me to thank Libuseng very, very much for giving this talk, especially at slightly short notice. So thank you, and hopefully you can come visit us in Johannesburg someday. At Wits Geotalk.
Definitely, I would love that. I would love that.
Great. Fantastic.
So for the student, they can just ask Robin or Dylan for my email address, and we can communicate.
Perfect. That's fantastic. Thanks, everyone. Next week, I believe we have Roger Schoon, who's giving a presentation on the Morensky Reef on the bush. Maybe Robin has to. I thought I could freestyle it. I thought no one would ask me questions. We'll check. There's a talk next week, but don't worry. We'll see you all next week, and you'll see the advert coming out in your email early next week. So thanks, everyone, and have a good long weekend.
Thank you.
I think next week is Roger. Robin, can I just end it? Can I just end the